Okay, so what we're going to do here is a problem where we're going to have to change from a Cartesian coordinate system into a cylindrical coordinate system. And we're going to do this by using Stokes' theorem. So Stokes' theorem again is we have our integral, some surface of the curl or effective function phi dot dA is going to be equal to our line integral. Okay, so this is the first thing we're going to do, and this is around some closed path. And the particular example we're going to do is for the vector field which is given above, and we're going to do it for a circular path of radius r. So if I just draw up my system, my various axes, so what we have here is the z, the y, and the x. And our path is going to lie in the xy plane. Okay. So what can we say about this path? Well, it's in the xy plane, so our infinitesimal displacement element, dl here, is going to be off in that direction. So it's going to be in the phi hat direction. Okay, so it's in the phi hat direction. So we have our infinitesimal displacement element vector is going to be equal to s d phi phi hat. What about our surface area element? So our surface area element dA, which is on the left hand side, that is going to be in the z direction, and what we have here is our s and our phi, which is changing. So here dA would be equal to s ds d phi z hat. Okay, so let's move on to the problem. So that's some important information that we need to know. So let's determine the curl of our vector field V. Okay, so the curl of V is going to be equal to the differential of the z component with respect to y, so 0 minus differential of the y component to z, which would be minus 1, by x hat, plus differential of the x component with respect to z, so 0 minus differential of the z component with respect to x, to x y hat, and the differential of the y component with respect to x, and differential of the x component with respect to y, z hat. So minus x hat minus 2x y hat plus z hat. Now we can see when we do the dot product of the curl of V with our infinitesimal area element, we're going to have a z hat dot z hat, and z hat in Cartesian and also cylindrical coordinate systems are the same. So we will have our integral between 0 and 2 pi for the phi, between 0 and r for the s of s ds d phi. The integral with respect to s is going to give us s squared over 2. So we will have our integral between 0 and 2 pi of r squared all over 2 d phi, and what we get here is pi r squared. Okay, so that's the first side done. Now we must do the second side to Stokes' theorem. And in order to do the second side, since what we have is our line element is going to be in the phi hat direction, we need to write v in cylindrical coordinates. Okay, now let's just see how we're going to do this. Okay, so we are going to have x is equal to s cos phi, y is equal to s sine phi, and z is equal to z. Okay, so we're writing our Cartesian coordinates now in cylindrical form. What about x hat or y hat or z hat? So x hat is going to be equal to cos phi s hat minus sine phi phi hat. Y hat, now all of these you can get in fighting Griffiths, is equal to sine phi s hat plus cos phi phi hat, and z hat is equal to z hat. Okay, so what are we going to do? What we want to do is just put these into our vector field V. So remember V. So we have V is equal to minus y x hat plus z y hat plus x squared z hat plus x squared z hat. Okay, so that's okay. I'm just making it a bit easier writing it over there. So, and we just put our components in. Okay, so what do we get? So writing this in cylindrical form, V is going to be equal to minus S sine phi by cos phi s hat minus sine phi phi hat plus z by sine phi s hat plus cos phi phi hat plus s squared cos squared phi z hat. Okay, so there we have it. We've written V in cylindrical forms. Now we have V dot dl. Now remember, dl, infinitesimal displacement element vector, for this around the path, which is in the xy plane, is given by s d phi phi hat. Okay. So V dot dl is going to be equal to minus by minus. We've got a s into s sine squared phi plus z cos phi d phi. Okay, so what else do we know here? Well, z is equal to 0 because we're in the xy plane. S is equal to r, which is our radius. So this means that v dot dl is going to be equal to r squared sine squared phi d phi. Okay, so now just for our final step, we must integrate this. So our integral is going to be between 0 and 2 pi for r squared sine squared phi d phi. So v dot dl, or on our closed path, is going to be equal to the integral of sine squared phi between 0 and 2 pi is equal to pi, so we have pi r squared. Okay, so this is the final answer that we get for this side. And what we see is that Stokes' theorem holds because we also got a pi r squared over here. Okay, so I hope that helps with demonstrating how to convert from a Cartesian coordinates to cylindrical coordinates.